In this topic, I'm going to talk about why the wind blows in the way that it does, or in the direction that it does. But first, I want to talk a little bit about what drives the wind. What makes the wind blow at all in the first place? And for that, I've asked Erin, who works in the lab with me, to give us a little demonstration.
Hi, I'm Erin. I work in the lab with Roberta, and today I'm going to be showing you one of the flasks that we use for sampling seawater. So this flask here is completely empty. I used a very strong vacuum to pull everything out of it, including air. And there's little black rings here that help stop outside air from getting into the flask before I'm ready to sample into it.
Okay, now the next thing Erin's going to do is open up that flask. Okay, so let's see what's going to happen.
So give a listen to what happens when I open the flask and expose the inside to air. Whoosh.
Okay, did you hear the whoosh? Right, so what was happening there? In the flask, we had nothing at all, essentially 0 atmospheric pressure inside the flask. And outside the flask, we have regular sea level pressure around 1,000 hectopascals. So when the barrier between them is removed, then air rushes from the high pressure to the low pressure. And that's what drives wind. Right? Air is moving from high pressure to low pressure, or there's a force in that direction. We call that force the pressure gradient force. That's its official name. You're welcome to think about it as there's just a difference in pressure. Okay, and this pressure gradient force is the driving force behind wind. That's why wind blows. Those differences in atmospheric pressure that we were just talking about in our last module along the surface of the Earth, those are the pressure gradient forces that we're talking about here. Now, before you started this video, I asked you to think about this idea. Right? Here we're seeing a variation in atmospheric pressure, and at the bottom we have higher atmospheric pressure, so towards the south, and then marching up there are different lines, and each line indicates lower atmospheric pressure at those locations till the top where we have the lowest atmospheric pressure. These are all at the same altitude above North America, so we're in the northern hemisphere here. So I asked you to think about which way do you expect wind to blow in this example. And you can consider the pressure gradient force, and there's another force that we've been talking about, the Coriolis force. Both of those come into play here. So if you haven't thought about it yet, or you want to rethink it, go ahead and pause the video now. Okay, so let's see what the answer is. The wind blows from west to east in this situation. Now, it's not the answer that many students think about, so I want to carefully go through why we see something that looks like that. Here we have that same diagram, but showing us these two forces. And you can see on the left side here, right, kind of an imaginary situation where the air parcel starts out stationary. So imagine first, even though this doesn't really happen, it really helps to think about it as though it does. Think about the air parcel starting out totally stationary. And then the only force when it's not moving is the pressure gradient force, which in this case is always going to point from the south to the north in this particular example. Now, the wind starts to move towards the north, and as soon as it does, now the Coriolis force acts to its right. So in the next diagram there, just sort of one over, we see the pressure gradient force still acting towards the north, but the Coriolis force acting a little bit towards the southeast here, and the wind started to be turned by the fact that these forces are acting in different directions. If we go a little bit further on, we see there that the wind has turned a little bit more. The Coriolis force is pointing almost south, but not quite, and the pressure gradient force is still pointing upward. We go a little bit more, and now we see that the wind has totally turned, and it's going from west to east. The pressure gradient force is towards the north, and the Coriolis force is toward the south. They're perfectly balancing each other. Now, you could do this little dance too in your own apartment or house to feel the effect. Okay, so I'm going to come over here and give myself a little bit of room, and the highest pressure is going to be behind me, and the lowest pressure is going to be out there where you guys are viewing me. Okay, and I'm an air parcel. So where's the pressure gradient force? Well, it's pointing towards you, right? That's the pressure gradient force. So if I start out stationary, then that's the only force acting on me. But as soon as I start to move, the Coriolis force acts over any motion happening on large scale. So as soon as me, the air parcel, starts to move, the Coriolis force starts to affect me. And we're going to imagine the same example. Coriolis force is acting to my right. This is my right hand over here. It looks a little bit funny because you're viewing me from the other direction. All right, but here's my right hand over here. And so it's pointing this way. Now, imagine someone's tugging me this way and someone else is tugging me this way. I'm not going to be able to just keep walking towards you because this tug over here, right? I'm going to start to turn a little bit. Now the pressure gradient force is still pointed towards you guys where the low pressure is. Coriolis force is acting towards the right, but now it's pointing, not perpendicular to the pressure gradient force anymore, but still not parallel to it. And so I'm still being pulled in two directions here, and I'm going to turn a little bit more, right? Now I'm almost turned all the way. Pressure gradient force still to you guys. Coriolis force still to my exact right, 90 degrees to where I'm facing. And it's going to pull me a little bit more until I'm right like this. Now the pressure gradient force is pointing to you guys still. Coriolis force is pointed back behind me here, but 90 degrees to the direction that I'm facing. And I'm not going to spin anymore because I've got an equal force pulling me in each direction. I'm still moving, but I'm not spinning. Okay, so try it yourself. Do it in your living room. Feel what it's like to have these two forces move so that you're not going to keep going straight towards where the low pressure is. Instead, you'll turn so that those two forces are going to balance. So if we come back to this figure now, we can really see how that's going to happen to create this turning wind. And what we see is that the wind will continue to turn until it's flowing parallel to those lines of constant pressure. When that's true, the pressure gradient force and the Coriolis force are opposing each other, so the wind won't spin either one direction or the other. The two are exactly opposing each other, and it's still moving, in this case, from the west towards the east. Now, I want to go through sort of some steps of how you figure out the wind direction. If you don't have that nice diagram sitting in front of you, you're going to do it on paper. There's two things we always have to think about when we're figuring out wind direction. The first, we better know what the atmospheric pressure is. Where is it high? Where is it low? And we've got to know what hemisphere you're in. Remember, the Coriolis force acts to the right in the northern hemisphere and acts to the left in the southern hemisphere. So we definitely need to know what hemisphere we're thinking about in order to know which direction the Coriolis force is going to act. Now I want to go through an example on paper to show you how to do that. Now let's use the same example that we just did, but I'll show you how to do it on paper. Okay, so first I draw lines indicating my different atmospheric pressure. So I have a high atmospheric pressure down here in the south, and I have a low atmospheric pressure up here in the north. And really I'm going to break these up into two steps. So this is step one that I'm working on right now. Now I do the kind of thing that we were just talking about. I think about a stationary air parcel that's going to try to move from the high to the low, and it's going to bend to the right because of the Coriolis force. So I start my arrow going, and I bend it over to the right until it's parallel to these lines of constant pressure. Now, as we said before, it's not like we ever really see a stationary air parcel that can just start suddenly moving. So this step is really to give you a sense of which direction it should go. But then in step two, we can think about which direction is it actually moving. Again, these lines are my atmospheric pressures. I've got high pressure at the south and low pressure here at the north. And so The lines that are in the upper atmosphere will make purple. The direction of the wind in the upper atmosphere is going to be parallel to these lines of constant pressure. So if I have north up near the top of my figure here, then this upper atmosphere wind is traveling from the west towards the east. Now let's do one more example, still in the northern hemisphere, but I'm going to put the high pressure in the north and the low pressure in the south. So I have my low pressure down here, my high pressure up here, and north is near the top of my figure. Now, to figure out which direction the wind is going to go here, I actually want to turn my piece of paper around so that the high pressure is down at the bottom, the low pressure is at the top. And now I'll think again about my stationary wind. If it's going to start out moving as though it'll go from the high towards the low and then bend to the right until it's parallel to these lines of constant pressure. And now I can see that this wind is going to flow from the east towards the west. Again, this is step one. So step one is about figuring out the direction from a stationary situation, but really we don't really ever see that. So then we move on to step two, put our lines back in for constant pressure. And my upper atmosphere wind in this case will flow parallel to lines of constant pressure and from east to west. Now let's apply this concept of thinking about what drives wind directions at our latitudes here around Victoria and Vancouver. We are around 48 degrees north latitude. That means that that high pressure zone that we talked about being around 30 degrees north, that's south of us, and the low pressure zone that's generally around 6 degrees north, that's north of us. And so we're usually experiencing the same situation in our first example, where the high pressure is at the south, the low pressure is at the north, and so the wind is going to travel from the west towards the east. That means we get most of our weather coming off of the Pacific Ocean, and that makes our climate a lot more moderate here in the Victoria and Vancouver region. These winds that are coming from the west, we call them the westerlies, and that's because winds are always named for the direction from which they come. So these are the westerlies, but if we go farther north, we find that the winds there are blowing from the east, and we call those the polar easterlies. Now, mostly what we've been talking about so far is what happens with wind direction up aloft away from the surface of the planet. And that's because when we get close to the surface of the planet, we get close to the ground, then there's a third force that we have to think about, and that's friction. So imagine a bumpy surface. We've got forests and buildings and hills and mountains, and as the wind blows over it, that roughness slows it down. It creates friction, and that's a third important force that we have to think about. That force varies in different places, right? Over the ocean is just not anywhere near as bumpy as the land, so their friction is much less than we see over the land surface. So when we think about wind directions near the ground surface, now we have one more force to take into account. In the upper atmosphere, the pressure gradient force and the Coriolis force were the two we had to think about. But now near the surface, we have to add friction as well. The way to think about it is that we saw that in the upper atmosphere, the wind would flow parallel to those lines of constant pressure. So I always figure out first, which direction is that going to be? And then, in the case of the surface winds, if we add the effective friction, it essentially just tilts the wind direction a little bit towards the low pressure here. So if it was this way, now it's tilted a little bit more, a little bit upward here towards the north, because the low pressure is in the north in this particular example. Okay, so what you want to think about is first figure out the wind direction in the upper atmosphere, and then just tilt your arrow a little bit towards the low pressure zone. Next up, I want to show you how to construct a map sort of summarizing all the things that we've talked about. And we'll have the atmospheric circulation cells, precipitation and dry weather, atmospheric pressure, and surface winds all summarized in one diagram.